Hello everyone, my name is Soumyajit Chakraborty. I am a MS scholar in the Department of Electrical Engineering. My topic today is Navigating Tomorrow, Exploring AI's Role in Autonomous Driving. So whenever we say this word autonomous vehicle, these fancy images of this car comes across our mind, right? Whether it is some full self-driving car built by Waymo on the left, or whether it is robotaxi built by Vox on the right. But first thing first, do we need self-driving cars at all? So if I want to answer this very simply, yes, we do need self-driving cars because it will make our life much more convenient since we don't have to drive. And moreover, it will increase road safety, it will reduce traffic congestion, it will reduce driving related stress, and overall it will save times. So, but what is going on inside an autonomous vehicle? So today in this talk, we'll go inside what is going on under the hood of an autonomous driving system and how AI can help us in building such one. So before going into the details of autonomous driving system, I like everybody to think how we humans drive. So we have eyes through which we are perceiving the environment. And our eyes and brains are interconnected in such a way that we are making a lot of perception tasks subconsciously that we are not realizing. So whenever we are moving, so whenever there is a congested road around us, we are trying to slow down. And whenever we have some vacant place, whether the road ahead of us is vacant or not, or whether the car in front of us is slowing down and speeding up. So after this, all of these subconscious perception tasks, we are trying to make decision. Like if the road ahead of us is vacant, or if the road ahead is congested, then we are trying to change lane to the next and try to move faster. And then we apply control accordingly that lies outside of our body. Like if you want to accelerate, if you want to move faster, we accelerate. If you want to move slower, we put brake. If you want to change lane, we steer. So if I want an autonomous driving system to replace an human, it should have these four major components, right? A vehicle sensor system, then it should have the perception module, a decision making or planning module, and lastly control. The vehicle sensor system can have a single camera or maybe multiple cameras depending on its use case, and each sensor has each of their advantage and disadvantage. It can have a front camera, it can have only a front camera to see what is there in the front, or it can have a multiple camera mounted all over the car to get a 360 view. It can have LiDAR, radar, it can have GPS for global positioning, or IMU for local navigation. Then it has a perception module that does all these perception tasks, like whether determining the free space in the lane ahead of us, detecting other obstacles and other cars in the road, and also trying to estimate their trajectory. And then we have the decision making and planning control. So can you see that there is a lot of intelligence that is required, especially in this decision making and planning module, which is in turn dependent on the perception module. So here AI can play an important role in making driving decisions. And when AI are being incorporated in autonomous driving system, they give rise to a different paradigm of driving called end-to-end driving. So in this end-to-end driving, all of this perception, decision-making block had been fused into a single combined block, which is directly making driving decision from the sensor data. So in this end-to-end driving block paradigm, we have the vehicle sensor system. From vehicle sensor system, we can get any type of data depending what vehicle sensor system we have. Then this sensor data have been directly fed into a single combined block, and these single combined blocks are determining the control action to drive the car. So what is the objective that I'm gonna talk about in this talk? So we want to design how to drive a vehicle in an end-to-end autonomous driving manner in a highway traffic scenario that is trying to navigate in a heterogeneous traffic which has a single autonomous vehicle and all other human-driven vehicles. And we also study the efficacy of different sensor data that we can use for autonomous driving. So now I'm going to present you my end-to-end autonomous driving architecture. So this autonomous driving architecture is a two-fold framework which has a two main component. One is the RL agent and another is the hierarchical control architecture. So the RL agent or the reinforcement learning agent, which is the AI agent that I'm talking about, is getting the sensor data from this vehicle sensor system that are representing the environment, and it is making these high level driving decisions directly from the sensor data. So all of the intelligence that I'm talking about is being confined to this RL agent. And then the high level driving decision that the RL agent is provided is passed on to this hierarchical control architecture, which has a high level controller and low level controller. So this high level controller will take these high level driving decisions like say turn left, turn right, accelerate, decelerate, and it will determine the actual lane and the velocity set points. Let's say if the vehicle is currently moving at 20 km per hour, and if the RL agent gives an like high level driving decision to accelerate, then the high level controller will determine the next set point at say 25 km per hour. And then all of this set point data will be passed on to this low level controller, which will determine the actual throttle and the steering values to drive the car. And then this whole process will goes on in a cyclic manner. So before going into the details of that RL agent, I like to give a small introduction to the reinforcement learning problem. So in reinforcement learning, is a learning paradigm where every problem can be formulated in a Markov decision process. A typical Markov decision process consists of set of environment or agent states, a set of action, a probability of transition, and the reward that we get in the transition. Let me give an analogy for a better understanding. Let's say we have a robot that is the AI agent, and depending on the task that robot want to do, we will define a particular set of states and environment states and agent states. And then the robot will take an action, and it will be implemented in the real world, and because of the probability of transition, it will transit to a new state. And whether that action the robot took was good or not, it will get a reward. If the action it took was good, then it will take a positive reward, a better reward. If the action it took was not good, it will take a negative penalty. So that's how the robot is trying to learn by a trial and error method, like which action it should take in every step. So what is the motive of the reinforcement learning? Like our simple motive is to learn a policy. So if I want to put this simply, the policy is the mapping from state and action. Like if you're in a certain state, what action shall I take? That's it, the policy. But how I can learn the policy is by evaluating the state action value function, or Q value in short. So what is Q value? So Q value, if I want to put it very simply, Q value determines the quality of the action the agent takes at a particular state. I mean, it's a Q value of a particular state action pair is high. That means if the agent takes that action, it will get a very high reward in long-term future. And if the Q value of a particular state action pair is low, then the reward it will get gonna be pure. So, so this is just expressed as an expectation of the future reward. So now we are trying to formulate our autonomous driving problem into a Markov decision process. Since this problem of autonomous driving is hard, so that's why we are not explicitly defining what our state should be. Rather than we are trying to learn the states. How we are learning the state? We are taking the sensor data, this high dimensional sensor data, whatever it is, we are passing it to a deep neural network. And this deep neural network is trying to extract some low dimensional state vector from this high dimensional sensor data. So this low dimensional latent feature that we are getting from this deep neural network are our state vector. So here the deep neural network is acting as a kind of encoder that encodes from the high dimensional data from a low dimensional data. For actions, we have some high discrete level actions like turn left, turn right, accelerate, decelerate, and move at a constant speed. And for reward function, we have a reward function that has a two component, which is a collision reward and a full speed reward. So full speed reward is acting as a positive feedback that promotes the RL agent that it can move at a high speed, and a collision reward is acting as a kind of penalty that the robot will receive if it is collide with other vehicles in the environment. So now I'm going to present is my high-level working of the reinforcement learning agent. So we can get any type of, like, whatever the sensor system we have mounted on the car, we can get any kind of sensor data. It may be camera system, it may be LiDAR or radar data, or it may be data from vehicle to vehicle communication. Whatever it is, we are first passing into some deep neural network. And this deep neural network will extract the MDB states. So this is like states extraction through deep neural network, and this MDB state will be passed on to this feed-forward neural network, which will determine the Q value for all possible action corresponding to the current sensor data. So what this Q value will determine? So if the Q value of a particular action is high, that means this is a good action. If if the agent takes this action, it will get a better reward in the future. So now the decision making problem will come, where it will take the action corresponding to the highest Q value, and this action may be any of these 5 high-level action of turn left or right, accelerate, decelerate, or move at a constant speed. So now I'm gonna give you some introduction of a autonomous vehicle and versus a connected autonomous vehicle. So in autonomous vehicle, the vehicle is trying to maneuver autonomously only using its internal sensor data, like using camera or LiDAR. But if we leverage the power of connectivity, where every vehicles are connected by surrounding vehicles in the environment, and they are sharing each other position and velocity, then we move on to, and we are using that information to move autonomously. Then we move on to another paradigm called connected autonomous vehicles. So for the first case, where we are trying to drive only in autonomous motion, the sensor data that we are using are the top view image or bird's view images of the car, and that captures car and its surrounding neighborhood. And for that, we are using some convolution neural network based deep neural network architecture for extracting state vector. So we are passing this the top view stack of some consecutive top view images through this convolution neural network, and ultimately we are extracting the state vector, and that is connected to another fully connected layer that determines the Q value for all possible 5 actions. So we will take the action that corresponding to the highest Q value. Now I want to give us some analysis of the performance of autonomous driving using this camera image data. So, and for evaluation metric, we are using average episodic length, which denotes that how long the vehicle is able to move in the environment without any collision until the vehicle collide or the episode terminates, and it is measured in time. And also we study the performance of the autonomous driving by varying the size of the camera images that we are capturing, and by that I means that if you are starting with a low size image, that it will capture a very less surrounding image, neighborhood, and if I gradually increase that to high frame size, then it will capture a much more region around the vehicle. So we saw that when you are increasing the frame sizes from, say, for example, 50 cross 50 to 100 cross 50 to 150 cross 50, the average episodic length are increasing. Why? Because since we are increasing the frame size, the CNN is able to capture a much more region around the vehicle, and so it will able to capture the movement of more number of vehicles around this autonomous vehicle, and thus improving its overtaking characteristic. And that's why you are getting increasing average episodic length with increasing the frame size of the image. But this overtaking characteristic has a pitfall that I will come to it later. And the second case, when you are trying to navigate through a connected autonomous motion, and for this the sensor data that we are using is the relative position and the velocities of the surrounding neighboring vehicles around the neighboring vehicles around this autonomous vehicle. For this, we are using a simple multi-layer perceptron for extracting the state vector out of the sensor data matrix, and the similar to the previous architecture, we are determining the Q value from the state vector for all possible action, and we'll choose the action with the highest Q value. For the validation and verification of the RL agent working, we are implementing the whole working in a like the highway environment simulator, which is a 4 lanes. What we're trying to maneuver this green vehicle, which is the autonomous vehicle, through these blue vehicles, which are human-driven vehicles. Now we play the videos of the autonomous driving for both the cases where we are trying to drive in only autonomous manner and the connected autonomous manner. So here I am driving the vehicle is only autonomous manner, where it is using the camera images to drive the vehicle. We can see that the vehicle is like showing a very aggressive overtaking nature, and it is trying to overtake at all the traffic condition, and it is not trying to estimate the surrounding traffic that much good. Now I'm showing the autonomous driving video when I'm trying to drive with connected autonomous vehicle manner, where we are using the relative information and velocity of the surrounding vehicles to drive. Here the vehicle is showing a much more cooperative nature. The vehicle is not trying to overtake, it is slowing down, it is determining the surrounding traffic condition, and that's why it is resulting a much more episodic length and fewer collisions. So if I summarize my talk, what can be the main takeaway? So we saw that how we can build an end-to-end autonomous driving to drive in a highway environment with reinforcement learning, and how this end-to-end autonomous driving system can be generalized so that we can use it to any type of sensor data. And we also saw that how we can leverage the power of connectivity and to drive in connected autonomous motion rather than driving in a only egoistic way. Thank you.